Hi, and welcome to Unit 8. It says 9, that's crazy talk. Unit 8 is forces, which is the natural extension of motion. They pair together very well, and we will do a lot of similar experiments and labs this unit like we did last unit. We're going to take notes today, just dive in, and make sure that your note guide gets filled out. With these, pause the note guide if I'm going too fast, which I get to do because it's a video recording. Here we go. So, force is when you do some sort of action on a body or a thing in order to change the thing's state of rest or motion. A push, a pull, a bump that will change something's direction, stop it from moving if it's moving, or make it start moving if it stops. Those are considered forces, and they can be on any body or thing. Forces have magnitude and direction, so that is important. We call them vectors. So something like this has a magnitude and direction. We'll just say that the magnitude that would be like, let's just say it's 10, and the direction would be to the right or the east. And then this one would be another force, but this one you can see would have a magnitude of maybe 20, and it would be also in the same direction. So that's what forces look like when we start drawing them. That's kind of what we'll do. So forces have magnitude and direction. And objects that are subject to balanced force, which means like a right side pushing on the left side pushing in opposite directions, they either don't move or they move at constant velocity. An unbalanced force must be present to cause any change in an object's state or motion or rest. So if my clock is sitting on top of my dresser and I push it off, it was staying there, but the unbalanced force causes it to now move. The person responsible for relating forces in motion was Sir Isaac Newton in 1687, and he was just over 20, and he had to invent calculus to prove himself right. Maybe you have seen or heard that sort of like, I don't know what you would call it, that like myth that like an apple fell on his head and then he kind of like was like, oh, gravity. Well, this is the first person to sort of relate all those things. And again, he had to invent his own math to make it happen. So there's 3 laws of motion, and they still hold true to this day. The first one states that an object at rest remains at rest, and an object in motion remains in motion unless it experiences an unbalanced force. So something's going to stay moving or stay not moving unless you do something to it. That's called the law of inertia. The law of inertia is when things will stay at rest or when they will keep moving. That's basically what inertia is, which I think there's some notes on that in a second. The second law for Newton states that a force is equal to mass times acceleration. So this is when you can, if you have something that's moving and it has some acceleration, then it's going to have a force. Or you can make something move by accelerating it with a force. All of these are different ways you can express Newton's second law, which is force equals mass times acceleration. There's a triangle in there we're going to get to at the end that we'll use pretty extensively for this unit. And Newton's third law, maybe you've heard of this one, is that for every action there's an equal and opposite reaction. So if I kick the wall with my foot with a certain amount of force, the wall kicks my foot back with the same amount of force. If I'm going to send a rocket ship up to space, then I have to send some fuel out the other end, the other direction, to make it go up. Okay, and every action is an equal and opposite reaction. We're going to look at 2 laws today and then come back to Newton's third law a little bit later. So let's look at the first law. Objects in motion tend to stay in motion. We call this the law of inertia. And I think you probably saw it up there, but inertia is the tendency of an object to resist being moved, or if it's already moving, to resist a change in speed or direction until an outside force acts on that object. And next time I see you, we'll do some demonstrations with that, and maybe you'll see some on video later. But inertia is basically things that are in motion tend to stay in motion, things that are at rest tend to stay at rest unless you do something to change that. Inertia is related to a mass, so mass is a measure of inertia. More mass means more inertia. Mass is not weight, though. That's an important distinction. Mass is a measure of how much stuff is inside of an object. Okay, so like the amount of stuff inside of me is my mass, and that doesn't change whether I'm here or whether I'm on the moon. Now, it's kind of a silly distinction because, we're not ever going to travel to the moon, I don't think. Maybe you will. It'd be pretty sick if you did. But the distinction is important for when you're doing physics and speaking about the universe. So mass is the amount of stuff inside of an object, but your weight changes depending on gravity. Weight is your mass times the acceleration of gravity. So your weight on Earth is not the same as it does on the moon because the acceleration of gravity on the moon is different, okay? Or your weight here is not the same as it is in the sun, again, because the gravity is different on the sun. So your mass never changes, but the weight can be different depending on where you are. An example of Newton's first law is when you're in a car and you suddenly stop at a red light. Stopping suddenly causes your body to press up against the seatbelt, which keeps you in the car. So objects in motion tend to stay in motion. I'm sure you could think of lots of other examples of that. I love my triangle here, but it looks like it's kind of got messed up. What a shame. So let's see. I'm going to erase my triangle or write over it here and make a new one for Newton's second law. So Newton's second law is force equals mass times acceleration. There is the equation right there. I think we've already seen it a couple times. Usually Newton's second law is just referred to as F equals ma. So force equals mass times acceleration. Let's redraw the triangle, but like really awesomely. Not my best. Something like this. It's not. It's kind of crooked. I failed you guys. Please forgive me. So you've seen triangles a couple times before. We're going to see a lot of them this semester. Your force goes here, equals mass times acceleration there. You all know how to use it, but in case you don't, you just highlight the one that you want. Like here, I want to solve for force, and so I do mass times acceleration. And you get the idea. You've used the triangle before. Force is measured in newtons. In newtons, 1 newton is equal to 1 kilogram times 1 meter per second squared. Not that you need to know the units, but that's how we measure force here in for physical science. There's lots of other ways to measure it as well. Pounds per square inch is a measure of force, pressure, as you can do all sorts of things. A simple example of calculating force, when a 7,500 pound or kilogram car accelerates at a rate of 25 meters per second squared. So if I want to calculate the force there, if I look at my equation, force equals mass times acceleration. And your mass is 7,500 kilograms, and your speed is 25 meters per second squared. And when you multiply those together, you get 187,500, and the label for this would be newtons. Okay, pretty easy to do those triangle problems for F equals ma because we've been doing lots of triangles problems before, and you're going to practice some of those in a little bit. But there's the first two forces we've got. The Newton's first law, the law of inertia, and also F equals ma. And we'll come back to, at the end, as you can see here, we'll come back to Newton's third law, which is that, wow, somewhere in here, who knows where it is, which is that every action has an equal and opposite reaction. But for now, we'll be done. This has been super fun. Everyone take care. Okay, see you soon. Bye.